Well, hello. Let's now get on to the second problem. This is about a three-dimensional system of differential equations, or a dynamical system, for which the variables are x of t, y of t, and z of t, and we can establish those using that. And we can differentiate those formally with respect to the independent variable t, like so. And the right-hand side of this system of differential equations is given by this, and we can establish that using this. And then finally, the set of differential equations can be obtained by subtracting the right-hand side vector from the vector of derivatives to give us this. And the problem number 93 is to find the general solution of this system of differential equations. So let's look at the solution. Well, we can see that the right-hand side vector is a linear combination of the variables, or each element of it is. So we should be able to write that as some matrix times the vector of variables. And that matrix is can be calculated by looking at the coefficient of one of the equation or right-hand side vectors involving one of the variables. And we can extract that using this, and we can look at this matrix using that. So in other words, the right-hand side vector is this matrix times the vector of variables. Well, what we do is we assume a solution of the form of a vector of constants times the exponential of some variable lambda times the independent variable. So let's take that solution there, and we can extract these coefficients by using this, and we can express the solution as an assignment rule using this. So this this tells us that x of t should be replaced by this, and we can differentiate that using this. So now we have an assignment rule for the derivatives, and we can apply those rules to our differential equations using this. And if we look at this, we can see that this is our exponential function. It multiplies every term in this vector and times some linear combination of the coefficients x, y, z. So let's get rid of the exponential term since it's never zero. So we do that. And if that function was to be a solution, then each term in this vector here should be zero. So these are a set of linear equations, so let's calculate the coefficients, or the coefficient matrix of that, and that's there. And of course the condition that this set of homogeneous linear equations has a solution is that this matrix must be singular, which means of course that its determinant, or the determinant of the coefficient matrix, which we can calculate here, has to be zero. And we can see that this is a cubic equation, and it clearly has a solution lambda equals -1. So we put lambda equals -1 in this, and we get 0, and we can see that's easily because we've got 24, -13, -10, and -1. And so we can write this equation as we can take out a factor of lambda plus 1, and then the result has to be a quadratic polynomial of this form, because the coefficient of lambda squared has to be 1 when we multiply it out, and the constant must also be 24. So the only thing that's unknown is the coefficient of lambda, and so let's do that. And now if we subtract that from the original form, then that should give us an equation for this parameter a we don't know. And if we look at this, we can see that indeed that's true if a is minus 11, so we solve that for a. The solution lambda equals 0 is not very interesting because it's a constant. So let's take our equation and replace a by its value, and we can see by inspection that the roots or the factors of this are lambda minus 3 and lambda minus 8. So they're the vector of eigenvalues, and we've got to test that to see that it indeed is correct. So we evaluate that for the second eigenvalue, and we get 0, and if we do it for the third eigenvalue, we get 0 also. So they are indeed the eigenvalues of the matrix. And for each of these eigenvalues, the coefficient vector x, y, z is the corresponding eigenvector, which we now proceed to find. So, so let's find the first one. So we take the coefficient matrix and we replace lambda by the first eigenvector. We can do that using this. And let's visualize that in matrix form using that. And now we apply row reduction to this matrix. Of course, the right-hand side vector is the 0 vector, so no matter what we do to that, we're not going to change it. So let's take, well, we need to find zeros here, and we can get zeros here by adding subtracting 3 times the first row from 8 times the second row, which is here, and then we can subtract the first row from 8 times the third row. So let's do that, and we can see that that produces zeros here and here. And now we want to apply row reduction to the second column. So in other words, we want to subtract 23 times the first row from 13 times the second row, and we can do that here. And we can see that the bottom row consists of zeros, as we expect, and now we can solve the system equations for the eigenvectors. The third element we can choose any way we like, and we can see that's, so let's choose it to be 1, and then if we look at the second row, or the second row, we can see that the equation will be satisfied with if the second variable is equal to the negative of the first one, so that's minus 1, and if we do that, then we can see that 8 times the first variable will be equal to the second variable plus the third variable, so that should be 0, and we better check that, and well, by multiplying it by the coefficient matrix, and indeed we do get the